everybody. Thank you for coming. Welcome to JAMS 8 2019, our annual symposium and dinner. It's good to have you here. My name is Yolanda and I will be your host today. Firstly, I'd like to acknowledge the Gadigal people of the Eora Nation, on whose land we meet today. I pay my respects to their elders, past, present and emerging, and also to all Aboriginal and Torres Strait Islander people here today. Here's Tom, our incoming Director of the JAMS Executive.
Thank you, Yolanda. Thank you all for coming. This is an amazing turnout. And as you can see, this was the first JAMS in 2010. So there's a few familiar faces, but lots of new faces. So if you look around you, you can see how much we've grown. So if you look around, you can see how much we've grown. So JAMS started 9 years ago now, which is a bit hard to believe. It started as a perceived niche for a seminar series and networking session, particularly supporting ECRs and MCRs in the non-clinical microbiology space, but since then we've grown to encompass all fields of microbiology and provide a forum for people to talk about microbiology in a nice relaxed environment. So as you can see, we've grown a lot since then, and we haven't just grown in terms of Sydney, we've started to grow nationally this year. So this is the first Brisbane JAMS, which occurred earlier this year. And those guys, led by Emma, who's going to talk later, have done a fantastic job of organising that. So it's great to see JAMS kicking off in other cities. And this is JAMS Adelaide, the organising committee, which was led by Rodrigo, who's sitting up the back there. Great job. And it was fantastic. Both of those JAMS have been getting awesome turnouts. So it's great to see JAMS growing at a national level. But it's not just growing nationally. This is JAMS Singapore, which happened a couple of months ago now. And got a massive turnout as well. So JAMS is what started 10 years ago with 9 years ago with a bunch of people having beer and pizza in the museum, is turning into a truly global organisation promoting microbial ecology, medical microbiology and networking in a friendly environment. So it's great to see JAMS growing at such a scale. And as incoming director, it's also my duty to thank Mike Mainfield. Stand up, Mike. Who is now the outgoing director, but he's establishing a board of trustees to oversee the expansion of JAMS. But he like to call it the Dead Jedis, or the JAMS Jedis, which I guess makes me Yoda. But no, we're not transparent. R2D2, if anything. That's going to stick out as the hashtag. But I hope everyone enjoys the seminars today. We've got an excellent lineup of speakers, and we have an excellent poster session with student posters, so enjoy that. And we have an excellent function tonight. So with that, I will pass back to Yolanda, and everyone enjoy yourselves, and I hope to chat to you all later. Cheers.
All right. Okay, so I'll give you a quick rundown of today. Today we're going to have 3 talks, followed by a few short presentations. Then we'll break at 2:10 for the student poster session, and we'll start back here again at 3:10 sharp. So that's up on level 4 in the Harborview room. Then we'll enjoy 3 more talks, and then we'll head on to dinner. So, as you know, we've introduced a new poster prize this year. The winner of this prize will have the most votes by 5 p.m. You'll see posters around that look like this on the left. All you need to do to vote is scan the QR code or go to the link, or you can head to our website, to that page there, and you can scan that QR code or head to that link instead. Okay. I'd like to warmly thank all of our sponsors, particularly those who are here today. And we've got a demonstration happening upstairs by Illumina, our platinum sponsor, who have been super supportive this whole time. We really appreciate all of the support we get. Later in the day, you'll be hearing from our platinum sponsor Illumina, and also our gold sponsor In Vitro. And I'd like to thank all of our academic sponsors. JAMS would not happen without the support of our sponsors, so we say thank you and welcome. I'd also like to bring your attention to the next ISME conference happening in Cape Town in August 2020, and you'll also find some ISME flyers on your chairs. I would also like to thank everybody on the JAMS committee team, who's helped make today happen. Mike, Tom, Shane, Federico, Deepa, and Hannah. Also, a big shout out to Nick Coleman. I don't think he's here yet, but he's helped out with the poster boards for our poster session, and Nathan Dankit, who's helping transport them. Finally, I'd like to thank you, our attendees, for being here with us today. It's a pleasure to be here with you. If you would like to tweet about today, you can use the JAMS 2019 hashtag and tag us, JAMS or GayU. Finally, some of today's talks will be streamed live on YouTube and made available through our YouTube channel. And there may also be a camera set up at some point to capture the audience as well. So just to let you know, your photo might be taken. Fire exits. If there is a fire, you'll hear an alarm. We'll head out these doors, but we'll wait for staff to come and collect us. Failing that, head over to Hyde Park. The toilets are just at the door and turn right, and you'll see a sign for them. Without further delay, I'd like to introduce our first speaker, Daniel Fallow. So, Daniel did his PhD on cell cycle regulation of phytoplankton at MIT, and he's been a researcher at CNRS, now a senior scientist working at the Station Biologique of Roscoff, France, since 1983. He initially developed applications of flow cytometry to measure picoplankton and bacteria abundance in the ocean. These methods have become de facto standards in oceanography. About 25 years ago, he focused on the diversity and ecology of eukaryotic phytoplankton, which had received very little attention. Bioengineering molecular approaches such as gene cloning, metabarcoding, and metagenomics. Daniel's current interests revolve around green algae, and he has always had a keen interest in data processing and software development, focusing recently on the open source R language. The group he initiated in Roscoff is now a global leader in plankton research with 35 researchers, postdocs, and students. He also created the 1998 Roscoff Culture Collection, which is now the biggest collection in the world for marine phytoplankton. Daniel has co-authored more than 150 papers, some of which are featured in journals such as Nature, Science, and PNAS. He received the CNRS Silver Medal and is a member of the European Molecular Biology Organization. He is currently spending 1 year at the Asian School of the Environment at NTU in Singapore as a visiting professor. I'd like to welcome Daniel to the stage. I'll let you drive. Perfect. Let's do that.
Okay. Thank you very much, Yolanda, and I really would like to thank JAMS for bringing me here, especially Yolanda, who interacted with me, Mike, and also Federico, who was the one that really got me here, trying to induce me. I'm not going to thank him too much because he made me change completely my talk. I gave a talk like 2 weeks ago in Singapore. I said, no, it doesn't go for JAMS, so I'm going to do something a bit different. And the title has been a bit changed also. I will go into a short history of phytoplankton, but I will focus more, where it should be for the camera, on the green algae. Maybe you can dim up the light, or it's okay?
Yeah, we can figure out how to do that.
I know most of you are microbiologists, but microbiology is not only about prokaryotes, archaea and bacteria, but also about protists. So I'm going first to introduce you to eukaryotic phytoplankton, then give some insights more into the green part of the phytoplankton, so the green algae. Then I will focus on one group called Mammalophysce, and I will try to say what's next, where we are going. So for many people, phytoplankton is mostly diatoms, here, and dinoflagellates. So they are big microalgae. They are still microalgae, but they are big in that sense that they range from 20 to 30 to 100 microns. One of the issues that came up in the 70s is that there were a big region of the ocean, as you can see from satellite, where phytoplankton biomass is very low, and when you go there with a microscope, you don't see diatoms and dinoflagellates. There are few, but most of the you don't see much actually. Still, this region has some chlorophyll, and the question was, what was this chlorophyll made of? So the first discovery was that of John Waterbury in 1979, when using epifluorescence microscopy, he discovered that
Would Helen Moore, please come to the admission desk.
oh, sorry. It's not for me. It's not for me. The mission desk right away. A bit puzzling. So John Waterbury discovered that there were a very tiny cyanobacteria called Synechococcus that inhabited these regions. And what really allowed him to see this was a shift in technology, basically epifluorescence microscopy. Then Penny Chisholm, a bit later, discovered Prochlorococcus, which is now known to be the most abundant cyanobacterium, even bacterium in the ocean, with the photosynthetic bacterium in the ocean, which abundance of 10 to the 5th cells per milliliter. But another break came with John Siebert in 1982, when using electron microscopy, he discovers that not only there were cyanobacteria in this kind of water, like Synechococcus here, but there were tiny eukaryotes, which size was the size of these cyanobacteria, actually. So this really changed completely our view of phytoplankton, and we moved to phycoplankton. So now we're thinking in terms of size range: phycoplankton 0.2 to 2 micron, nanoplankton from 2 to 20, microplankton from 20 to 200, and I'm going to focus there on the phycoplankton. So if you look at the tree of eukaryotes, you find that algae in general are spread throughout the tree. So most of the groups, except for the opisthokonts, where we are here, okay, the animal, this is us, there are some representative of algae. And phycoplankton, phycoeukaryotes are almost in all of these groups. So in all of these groups, there was an evolution in a reduction of cell size, which induced very, very, very small organisms. I'm going to walk through some of these. In 1980, Wenke Ekrem and Jan Trondsen discovered, for example, this algae called Bathycoccus. It's called Batty because it has been isolated from 100 meters of Naples. It's very small, 1.5 micron, and it bears scales on the cell. Another even more famous phytoplankton is Osteococcus. It's the smallest photosynthetic eukaryote known today. Its size is 0.8 micron, so it's really a big bacterium, but it's a eukaryote. It has everything: a nucleus, a chloroplast, a mitochondria, here, a Golgi apparatus. And it's called Osteo because it was isolated from a lagoon, the lagoon of Thau in the south of France, where they're growing oysters. So from Osteo. It's called Osteococcus tori because it's from the Thau lagoon. Another, now Osteococcus and Bathycoccus are green algae, And another group that was observing the phytoplankton also is this organism that we discovered in our scope, 1.5 micron, big flagella, and swimming very fast. That's why it's called volidomonas, because it's swimming very fast, very close to diatoms. A few years later, another type of organism was isolated. It's called Chiparma. This time, it's not flagellated. It's covered with silica plates. And it turns out that by sequencing the 18S, people have found, Japanese researchers actually have found that these two are very, very similar. So now, first it confirms that this phytoplankton is a sister group of diatoms because it is related to Chiparma with silica plates like diatoms. And also the hypothesis is that they may be part of a life cycle where you have like a diploid phase and a haploid phase. So many species have been discovered, but I'm going to focus on one group of phytoplankton, the green algae. So most of you probably know that there are two major lineages in algae. The green lineages, which led to the land plants, where we have the green algae, but also some related algae where there are green like chloroplasts, and then the red lineage, which originated from red algae, but which gave life to the dinoflagellates, to the diatoms, and to many, and more generally to the brown algae. So it's a bit confusing. We call it the red lineage, but most of the red lineage are in fact brown algae. Okay? So this group is super important, of course, in land because it gave rise to the land plants. But this group is was thought to be more important in oceanic waters because that's where the diatom and the dinoflagellates are part of. And Paul Frankowski, that many of you heard about, he just won like the Nobel Prize in Ecology last year, and he's in Australia. He's giving a talk somewhere in Australia, somewhere. Published this landmark paper, Why is the land green and the ocean red? And he asked some questions about the evolution of these two lineages, why one became almost not important in oceanic waters. But with the discovery of phytoplankton, actually, where a lot of the species belong to the green lineage, the question actually is the ocean really red? So that's the question that I tried to address in recent years. And for this, we use the power of metabarcoding. So metabarcoding is sequencing massively a given gene in natural populations. This has been used, of course, a lot for bacteria, but we have been in the last 10 years using it also repeatedly for eukaryotes. So I've been using two data sets which are global data sets, and that's also a change in recent years that we have become moving from local study to these massive studies for bacteria, of course, but also done for colonies. The first one is the Ocean Sampling Day, which was part of a European project called MicroB3, where people sample in the summer solstice, but so the northern hemisphere summer solstice, so here for the winter solstice, a range of about 150 stations, and it was in 2014. This project has been going on, so now there are more stations going on actually, and I think now there are about more than 200 stations that have been sampled in 2018. for all these stations, metabarcoding for 18S was done, and there was about 1 million sequence obtained for this survey. Another survey that we use is Tara Ocean, which maybe you didn't hear so much about here, but this is a French-led expedition that with a research vessel went around the world and collected basically more than 40 stations. There are more now, but this was at the time of the study, the stations that we had, 2 different depths and 4 different fractions. One of the big plus of the Tara data is that the coverage is incredible. For each sample, we have more than 2 million barcodes for each sample, like a normal survey would be like from 10,000 to 100,000 barcodes. So we tried to look at green algae in these data sets, and this was a work of my PhD student Margot, who defended at the end of 2017. So the first task was to assemble the existing sequence of green algae in marine waters and also in fresh water, and to annotate them, because one of the critical points that you need to address before doing any metabarcoding is to have a very good reference database. So we developed a database for a protease called PR2, and Margot initially looked at all the sequence from GenBank and re-annotated them and put them into PR2. So then we had the tools to annotate this metabarcode. And what we found actually, looking at OSD, but we look at other data, and it's always the same orders, magnitudes in marine waters. At least I'm not talking about freshwater, I'm not talking about soils, I'm just talking about marine waters. Is that flow phyta represent about 25% of the barcodes that we get in marine waters. So 25% actually of the phytoplankton is green. So the initial postulate of Paul Valkowski that the ocean was completely red is not really true. There is some green in the ocean. And moreover, this can go very high because in OSD we have some stations, especially in the oligotrophic ocean, where 95% of the metabarcodes, of the protease metabarcodes, are from green algae. So green algae can be super important. For example, this is of Nani. So they can be super important, especially in oligotrophic waters. So the question is now, we know that the ocean is not only red, it's green. So what are the shades of green? What kind of green algae do we have in the ocean? And this is work that Adriana Lopez dos Santos, who was a postdoc in my lab and who is now a professor at Nanyang Technological University in Singapore, did. So she compares the data from OSD, which is mostly coastal, to the data from Tara oceans, which are mostly oceanic. And she found that indeed the composition is very different. We have one group here called Mammilophyceae, and Mammilophyceae is the Osteococcus, Bathycoccus, as I just mentioned, very, very small green algae. And prasinophytes, which were then called prasinophytes grade 7, which are dominant in the ocean. Just to orientate you, and I'm giving some other talks, and I will mention more about this. This is now a new class of algae called Chlorpicophyceae. So prasinophytes grade 7 doesn't exist anymore. What you can see is that actually when you look, for example, at electron microscopy, they look the same. But we can't really distinguish them by phylogeny, by genomes. There are many ways to distinguish. So they are different, and their ecology is really different. So I'm going to focus now just on the green algae and on the Mammilophyceae, on the coastal ones. So, Mammalophysae, they are present basically in all coastal waters. If you look at the abundance, so the size of the circle is basically the percentage of Mammalophysae within Chlorophyta. Doesn't vary so much. There is some variation, but when we try to interpret, to look at the parameters that regulate this abundance, we don't find any clue. So we will need to go to a more finer detail. And here the message is that you have really to go into the detail to understand the ecology of these groups. If you stay at large levels, you don't understand anything. It's like saying that the ocean is full of alpha proteobacteria. Yeah, everybody knows this, okay? But so the ocean is full of diatom, full of dinoflagellate, but you don't understand anything when you say that. So you have to go a much deeper level, and for eukaryotes is going to the species level. So we have four major species within this Mammalophysae. Ostrococcus, the smallest eukaryotes, pointed micron. Batycoccus, here which has some nice scales, 1.5 micron. And Micromonas. I didn't mention Micromonas yet, but actually it's the first ever phytoplankton described in 1952 of Plymouth. They're very, very fine phycologists on the other side of the channel, on the south side of the channel in Roscoff, and Plymouth in the north side. So, as you can see, if we look at the barcodes from OSD, this is the OSD data, major genus is really Micromonas, followed by Ostrococcus, followed by Batycoccus. However, Batycoccus is much more prevalent in terms of its number of stations where you find. So basically, you go almost anywhere in the ocean, you are going to find Batycoccus. Ostrococcus, you find it only in warm water. So if you go to polar water, for example, you don't find Ostrococcus anymore. You find it in the tropics. And finally, Micromonas, you find it everywhere. More in coastal waters than in oceanic waters. You don't find it so much in coastal waters. But for example, off Singapore, we have Micromonas, but you have also Micromonas in the Beaufort Sea, and you have Micromonas under the ice. So it's a very ubiquitous genus. So if you want to look at its distribution, its ecological feature, you need to go a smaller level, a finer level, and that's the species. So let's go to Micromonas. So Micromonas, we have described a couple of years earlier, 4 species. 2 species were already described, Micromonas busia, which was from the 1952, Micromonas commoda, which was described like 3 years ago, and then we described 2 more species, Bravo and Polaris. As you can see again, they really look the same, although there is a slight difference. What we found is that the length of the flagellum actually is the only morphologic feature that allows you to distinguish these algae. But now when we use metabarcoding, instead of these 4 species, and also we have 2 candidate species, we can describe a really based not only on the tree but also on some sequence feature in the V4 region of the edginess. We can distinguish 9 cases of species. So for example, the species Commoda, we can split into 2 different cases. And when we look at the distribution, then things really begin to make sense when we use these clips. For example, I will just take 2 examples. Micromonas polaris, as its name is, because we find it in polar waters, you only find in polar waters. So you find it, also there are some report of it in the Antarctica. So you find it in the Beaufort Sea, you find it of Svalbard, for example. And so now this other clay that has no name yet called B5, it's a tropical clay. You only find in tropical waters, and especially you find off Singapore. So that's the message, is that we really need to go to this very fine detail if we want to understand the ecology of this process. And for green algae, I think we're getting there. So what's next? I think there are two things. First, 18S, of course, is a good marker. We can have finer marker like ITS. But we need now to go to the genomes, and especially to understand how the genomes is related to the environment. For example, this is Baticopus, which genome was sequenced in 212. And here, these are data from metagenomes of Baticopus. And what you can see is that there are some regions in the metagenome that are missing. So this is from a culture organism, and this is what we find in the ocean, different oceans, North Atlantic, Pacific, South Atlantic, and some genes are missing. So we have to understand why these genes are missing. There are some genes that are not really necessary under these conditions. So linking genomes to the environment, I think, is really the next frontier we need to address the ecology of this organism. The other area that we need to develop is interaction. So for example, this is a network of Brazil of different types of phytoplankton. And we can see, for example, that these two organisms which I mentioned repeatedly, Baticopus and Australopithecus, are closely linked. So why do we always find them together under these conditions? What's the link? Are there similar niches, or is there also reason to find them together? So we stop here. So green algae make 25% of the phytoplankton, roughly. I mean, this is just a number. This is going to change, of course, but if you remember one number from this talk, this is this one. We have Mammilophyceae, so green algae related to Mammilophyceae in coastal waters, Tropicophyceae, the old Prasino-7 in ocean waters. We can see now patterns, ecological patterns emerging, but we have really to go to the species or the clade level. What's next is linking genomes and environmental adaptation, and also study interaction. And I will stop here.
Wonderful, thank you. Okay, I'll open the floor for questions for Daniel.
So we were looking at Baticopus only, and we were recruiting actually the read. This is from Far Oceans data to the genomes that from culture genome, from culture. So basically, we don't know. I mean, we don't know. We try to find whether there were some. And in most of the cases, the missing genes are unknown. I mean, we don't know the function, so it's difficult to whether that's. So no, we are not. I think we still have. There are very few papers in contrast to bacteria on metagenomes of eukaryotes, because first there are not so many reference genomes actually. So I think really we should do more of these. So that's the next one here.
Any other questions?
question is that it's a little bit behind the bacterial stuff. So what would be the main reason for that? In terms of, you're just starting to link genomes and function and find, associations between different organisms. What's the kind of that?
Well, I think first, the crowd is a bit smaller. There are fewer people. Also, I think in some way, what drives actually a lot of microbial ecology is behind the scenes biotech. And, so we don't have so much pressure. But I think the other, and you can see it's like a 10-year difference between protists and bacteria. Like Giovannoni sequence, the first clone library from Giovannoni was 1990. The first same approach for eukaryotes was 10 years after. The first genome of bacteria and the first genome of eukaryotes is the same. So I think we have, but one thing is that for the genome especially, the complexity is much higher, okay, and it costs more, and it's hard. So now, these are small genomes, 20 base pair, but still it's a lot more than cyanobacteria, for example. So my colleague in Roscoff, I'm sharing an office with Fred Bartensky, who is working with Synechococcus. They have like 100 genomes of Synechococcus. We have like 2 genomes of Astrococcus. So that explains a lot of the difference. And also, this is a pen. When you do metagenomes in the ocean, you get mostly bacteria actually. So if you want to get metagenome of eukaryotes, you have to sequence to order of magnitude higher depths than for bacteria. So life is not so easy for us.
Any final questions for Daniel? Yeah.
So the example of the micromonas, Polaris and plate 95. It implies that it's temperature, or is it light, or what is the driver of that?
Well, in this case, I think it's really temperature. And I think the pattern we can see, especially in coastal waters, are more probably related to temperature. Then when we want to study other factors, we have to take gradients like from the coast to the ocean and look then at other data sets. But the data set from OSD, I think the most relevant factor is probably temperature. There is also salinity a little bit, but not salinity. So for example, we found some places which are restricted to lagoons because they are like brackish or they can withstand some differences.
Okay, all right. Please join me in thanking Daniel.